Let's think about this function. Now, what's happening is, you know, and this kind of came to the fore when we were doing the graphing topic not that long ago, real functions. You know about a whole bunch of different kinds of functions and relations as well, actually. You know what they look like. You know how to draw them. But when we've introduced this idea of like derivatives and differentiation, we've pretty much stuck to polynomials, right? We just started with very simple ones. And that's because this idea of differentiation, we want to nail it first. We want to nail first principles before we expand the repertoire. Before we think about, okay, look at all these other different kinds of functions that you actually are aware of. Come in, take a seat. And how do we differentiate those as well? So in some ways, in calculus, we're kind of now playing catch up, right? Where we know all of these kinds of functions, but we don't know how to differentiate all of them. We only know how to differentiate this little small subset. Okay. So we are learning ways of expanding our repertoire, and today is a really big one. Let's have a think about this function. Now, if we were to differentiate y equals 4x squared plus 1 all squared, okay? At the moment, what we need to think of is, well, okay, look, I have a, I know how to differentiate x squared. I can do that. It's just a power of x. I know how to do 4x squared. That's just a multiple of a power of x. I know how to do 1. Okay, but it's okay, take a seat. But in order to get this into something that I can work with, like this being squared, right? It's not just a sum or a multiple. I need to expand this out in order to get a sum or a multiple. Okay, so let's give this a go. It's just a perfect square. Let's expand it out. 4x squared, a plus b all squared is going to be a squared plus 2ab plus b squared, right? So what am I going to get? What am I going to write down first? 16x to the 4. That's the a squared. Then I'm going to get the 2ab in the middle, which will be 8x squared. And then there's just going to be a 1 hanging on the end. You happy with that? So far, so good. So if this is y, now I've got it in a form that at the moment I can differentiate. Now I can actually find the derivative. I can say, on this basis, dy and dx is equal to, and now these are all just sums and multiples, and we dealt with them yesterday, right? So 16x to the 4. What happens to that 4 up in the power? It comes out the front, multiply that by the coefficient that's already there, and becomes 64. And then the power goes down by 1. Right? Important to do it in that order, by the way, because you're not going to multiply by 3, you're going to multiply by 4, the power that it was before. Okay? That's the first term. Second term is just going to become, read it off. 2 is going to come out the front, become a 16. That's going to be x to the 1. So I'm done. Okay, and we already know, I'm going to stop writing because it becomes a bit of a trivial thing. When you see a constant, differentiating a constant, you can think about it in 2 ways. Number 1, differentiating a constant will give you 0. Okay. Or, secondly, if this was the function, right? What is the difference in gradient between this function and this function? And the answer is, there's no difference. This plus 1, it just moves the whole thing up. Doesn't contribute anything to the gradient, okay? So you can either think of it in terms of, you differentiate it, you get 0, or it doesn't contribute anything down here to our derivative. Okay, we're done, right? So this is all happy times. But it doesn't take too much effort to imagine a point where, in order to differentiate, like before we could even start this differentiating process, we had to expand, okay? Expanding was okay because the power was low. It was just 2. Squaring we're very good at, right? If it was cubed, you've done binomial, you could do that. It would take a bit more effort, but you could do it, okay? But as those powers start to get higher, it starts to become less and less practical. If it was 4, I think that's really rough. Like, I think 3 tests enough. If it was 5, you're sort of getting a bit, you know. And if it was, say, you know, I don't know, 30, you're just going to say, forget it, right? It would take me half an hour just to write out the expansion, let alone differentiate it. Okay? So we're not going to be demonstrating any particular skills here. So therefore, when we have high powers like this, we need to have better tools at our disposal than just, you know, expanding out and then differentiating. This expanding out and then differentiating, it's a little bit like, you know, trying to, if you've got a, you know, a big huge pot of soup, okay, and you've got like 20 people to feed, and you're trying to feed them, you're trying to ladle it out to everyone with a teaspoon. You're like, I'm just gonna be here forever, right? Surely there's a more efficient tool like you used to just go, and then here you go, bam, off you go, do the next one, okay? So here's what we're gonna do. Let's come back to this guy, right? What I see here is that this is not just one big function. I can think of it as, remember we were thinking about compound functions yesterday, right? We were thinking about what happens when you add different functions together, what happens when you multiply functions by numbers, okay? Here what I've got is one function in there, 4x squared plus 1, that's a function. Okay. And then I'm applying another function to that. I am squaring the whole thing. Squaring is a function, yeah? So I've got a function in here, and then to that function, I'm applying another function. I'm squaring it, okay? Yes.